Okay, and let's try to solve exercise number 11 from electricity and magnetism. Exercise number 11. Exercise number 11 from electricity and magnetism. Space between plates of parallel plate capacitor is filled with two dielectric layers. The dielectric layers are connected in series and have thicknesses D1 and D2. D1, D1 and D2. The relative permittivities of the electric layers are equal to epsilon 1 and epsilon 2. Epsilon 1 and epsilon 2. Epsilon 1 and epsilon 2. The area of each plate is equal to S. Area of each plate is equal to S. Find the capacitance of the capacitor and the area bound charge density. Area bound charge density of the layers interface if the voltage on capacitor is equal to U. Voltage is equal to U, and the electric field is directed from the layer 1 to layer 2. Okay, and first of all, I think it is necessary to draw a picture. With this capacitor. So we have parallel plate capacitor, left plate and right plate, and this these plates has area S, and the capacitor is filled with the electric two dielectric layers. Filled with two the electric layers. So the thickness of first layer is D1, and the thickness of second layer is D2. This is D2. This is D2. Oh, it is necessary to show this. So D1 and D second, D2. And here we have epsilon 1, and here we have epsilon 2. And electrostatic field is from layer 1 to layer 2. Is directed from layer 1 to the layer 2. So it can be shown in this way, with these arrows. So this will be electric field. It will be electric field between plates of parallel plate capacitor. Electric field. So and the electric displacement vector is D. Or electric displacement or electric induction. This is the same. Electrostatic field. So according to the direction of electrostatic field, we can say that here we have charge plus Q, and here we have charge minus Q. So first of all, it is necessary to define in first part of the exercise, it is necessary to find the capacitor of such system. Okay, and do you have any ideas how to do this? Do you have any ideas how to do this? So how to find the capacitance of this system? Okay, maybe it is necessary to remember. It is necessary to remember what we were speaking about capacitance on our lectures. On previous week. On previous week. So on previous week, and according to this, decide what to do with this system, because we have already took a few examples of calculating of capacitance for different systems. So we know method of doing this. We know method, so it is necessary to just to remember this method. And all steps of calculation of capacitance will be very similar. Will be very similar in every case. Okay, so what can we do in this situation? I think we can define first of all, we can calculate some parameters of electrostatic field between plates of capacitor, and then calculate connection between electric charge and potential difference, and then from this connection, from this formula, we can define capacitance. And to calculate electrostatic field parameters between plates, we can use Gauss flux theorem or Gauss law. Gauss flux theorem for electric displacement vector. So let's remember this. Let's write this Gauss flux theorem. Surface integral on a closed surface S of d ds is equal to electric charge inside closed surface S, and this is equal to triple integral. In general case, it will be triple integral. Vs is volume inside of closed surface S, Here we have rho Q, charge density, and multiplied by dV, and multiplied by dV, multiplied by dV, multiplied by dV. Okay, so do you have any ideas what to do? What will be the next step? How to use this Gauss flux theorem? How to use this? What is the first step? The first step is to define the type of symmetry of this system. Type of symmetry. And there are three types of symmetry. They are plane of symmetry, axis of symmetry, and center of symmetry. Okay, and which type do we have in our exercise? Plane of symmetry, axis of symmetry, or center of symmetry? How do you think? How do you think? Which type of symmetry we have in this situation? I think it is simple. I think it is simple uh, because, for example, plane of symmetry. Plane of symmetry. We have, for example, for rectangle. For rectangle. Why it has a plane of symmetry? Because we can write we can define two planes. We can define two planes that no not arrow. It will be we can define two planes that separate our rectangle in two equal parts. So rectangle has two planes of symmetry, and they are shown with dash line. Okay, and what about, for example, what about for cylinder? What about for cylinder, for example? What about for what about cylinder? What about cylinder? Cylinder 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 has, of course, it has axis of symmetry. Cylinder has axis of symmetry. Cylinder has axis of symmetry, and sphere or ball has center of symmetry. Okay, and which type of symmetry do we have for plane for parallel plate capacitor? Which type of symmetry do we have here? How do you think? Okay, dear students, do you hear me? Okay, again, does anybody hear me? No one. Okay, so I have interesting question. Why do I speaking about why am I speaking about physics here now? If anyone hear me, okay, no one hear me. Okay, but it is necessary. It is necessary to do my job. Okay, so this system has a plane of symmetry, of course, plane of symmetry, and for this case, the Gauss plane, Gauss surface will be two parallel planes. The optimal surface will be two parallel planes. So let's show them in picture. It will be two parallel planes. Two parallel planes, and both any of them has area S. And why this choice is optimal? Why this choice is optimal? Because the angle, there is a right angle between vector D and this surface. This is the first advantage, and as a result, we have that element of this surface, this element ds, will also be perpendicular to this surface. Will also be perpendicular to this surface. So according to this, we have that. According to this picture, we have that vector D has the same direction as vector ds. Has the same direction as vector ds. Okay, and from here we have that scalar product or dot product of vectors d and ds is equal to d ds and ds and cosine and cosine. What will be the angle? What will be the angle between vector d and ds if they have the same direction? What will be the angle in this case between them? How do you think? What will be the angle between vector d and ds if they have the same direction? So what should I write here? What should I write here? How do you think? I think it is simple. I can write. I can draw this. So, for example, here we have vector d, and here we also have vector ds. We also have vector ds. ds. We also have vector ds. Okay, so according to this, uh, what should I write here? According to this picture, this cosine of angle between vectors d and ds. Okay, again, can you hear me? Dear students, yes, you can hear me, but maybe you have some questions. If something is unclear, if something is difficult to understand, you may ask questions in this case. Okay, because if you want to have if you want to have good grades at the end of the semester, you should be a little bit more active. You should be a little bit more active on practices, and maybe answer some questions, and to do homeworks, because because anyone doesn't do any homework, and during this semester I didn't I didn't obtain any homework from you. So this is bad situation, I think. This is bad situation. So uh, how can you get good grades if you are not active in your education? Okay, if two vectors have the same direction, the angle between them will be zero. And cosine of zero is equal to what will be here? Can you remember from school maybe cosine of 0 degrees or cosine of 0 radians? Result will be the same. Okay. Okay, it will be 1. It will be 1. Yes. Yes, it will be 1. It will be 1. It will be 1. Yeah, good. So here we have just absolute values of this vector d and ds. D and ds. Okay, and if we calculated this scalar product, not calculated, but we simplified it a lot. We proved that this scalar product can be written, can be calculated just as a product of absolute values. So scalar product in this case is equal to product of absolute values of this vector. So according to this, we can write that this integral is equal to similar, very similar integral, but without vectors. It looks very similar, but it is much simpler. It is much simpler than it was before, because it doesn't contain any vector. Okay, and moreover, the field between plates of parallel plate capacitor is homogeneous. It means that D doesn't depend on ds. And according to this, we can write D outside of the integral. So we will have S ds. We will have ds. Okay, and how to calculate this integral? Can you remember? Can you remember from our previous lessons? How to calculate this integral? But this integral, I'll write it separately. This integral is just a sum, according to the definition of integral. This is just a sum of this element of area. Yes. So if we add all these elements, what will we obtain? Maybe you can write this. What will we have here? According to the picture. Difficult situation. It will be area that is crossed by lines of electrostatic field. by lines of electrostatic field. So this will be area. This will be area of this surface. This will be area of this surface that is shown with dash line. So it is just equal to S. It is equal to S. So very simple. Very simple. So it will be D multiplied by S. So we have got rid of surface integral. We have got rid of surface integral, and this is a very good result. This is a very good result because we still don't know D. We don't know electric displacement vector, but we managed to get rid of the surface integral, and this is great. This is great. Okay, and it is necessary to say that these actions, these actions, these actions are the same for any problem that can be solved with Gauss flux theorem. These actions will be the same. So it is necessary just to remember or write this, and these actions will be the same for any problem that can be solved with Gauss flux theorem. Okay, so we have calculated the integral in left part of theorem, and the next step is to calculate the right part of this theorem. And what is QS? QS is electric charge inside a closed surface. Electric charge inside closed surface. So if I am close this surface, if I close this surface, what charge will be inside this surface? How do you think? Okay, let's write another picture. If closed surface looks like this, if closed surface looks like this surface S, and for example, here we have Q1, here we have Q2, here we have also Q3, and somewhere here we have Q4. The charge QS in this situation, charge inside closed surface S, charge QS will be Q2 plus Q3. Okay, do you understand this? Yes. Okay. Okay, that's great. Okay, that's great. And let's return to our previous picture. What charge will be in this case? charge inside closed surface. Okay, if we compare this picture and this, so what charge will be for our exercise? Charge inside closed surface S. Okay, and what charges do we have in our system? I think we have just only two charges. We have just only two charges, minus Q and plus Q and plus Q. And one of them is inside closed surface, and one of them is outside of the closed surface. So we need charge inside the closed surface. What charge will be inside? Yes, it will be plus Q. It will be plus Q, of course. It will be plus Q. Will be plus Q. So we can we have defined that charge will be plus Q, or this is the same as just Q. This is the same as just Q. So we have so simple answer in this situation. Okay, we have charge Q inside closed surface S. Okay, and let's substitute these results into our Gauss-Flux theorem. Let's use this result in our Gauss-Flux theorem. So I will substitute this here according to this arrow, and from here we will have that ds is equal to q, and so from here we can obtain that d is equal to q divided by s. So this is electric displace absolute value of electric displacement vector. Inside this parallel plate capacitor. Okay, do you have any questions about this? No questions. Okay, so if there are no questions, I will remove some things that we don't need anymore. So I don't need this. You don't need this, and it can be It can be removed. It can be removed from our picture. And this Gauss-Flux theorem can also be removed. It can also be removed from our picture. So we have proved that electric displacement vector is equal to charge q divided by area S. Such a simple result. Okay, but the next step that we need to do is to define electric field intensity. Electric field intensity. Okay, so can you remember connection between electric displacement vector and the intensity of electric field, or electric field intensity? Connection between electric field intensity and electric displacement vector. So the next step is to define. The next step is to calculate, is to find electric field intensity E1 in first layer and electric field intensity in second layer. So how do you think? How to define these electric field intensities? But we just can remember that electric displacement vector is equal to epsilon 0 E. Epsilon 0 E. And the electric is isotropic. So it can be written without vectors for isotropic dielectric. So D is equal to epsilon 0 E, and from here we have that oh, no, there are no vectors. E, absolute value of electric field intensity will be equal to D divided by epsilon 0. Epsilon 0. It will be epsilon 0. Okay, do you have any questions about this? No questions. Okay, so for electric field intensity in the first layer, we will have D divided by epsilon 1, epsilon 0, epsilon 1, epsilon 0, and it will be equal to Q divided by epsilon 1, epsilon 0, epsilon 1, epsilon 0, s. Epsilon 1, epsilon 0, s. And in a very similar way, we can define uh, this uh, very similar result, but with lower index, 2 instead of 1. Okay, do you have any questions about this? No questions. No questions. Okay, if there are no questions, 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 I will move this here. So we have obtained electric absolute value of electric field intensity. Okay, and the next question is how to define the connection between electric charge and the potential difference So we have to derive potential difference from here. To do this, so how can we define potential difference? With or how to connect potential difference with values. How to connect potential difference with these values. Mhm. Okay, according to the definition, according to the, one of definitions, it can be calculated. Via integral. Via integral from E d r, E and dr, and here we have for example d1. No, here we have 0, and upper limit will be d1 plus d2, d1 plus d2, d1 plus d2. Okay, the d1 plus d2. Okay, and the next step. How can we use this? Because this is a general formula. It contains electrostatic field intensity E, but we have two values. E1 and E2. So what can we do in this case? But we can just separate this integral. We can just write this via two integrals. So first integral will be from 0 to d1, thickness of first layer to d1, and here we will have electric field intensity in first layer, dr. Okay, and plus integral of d1 vector, and to here we have d1 plus d2 e2 dr. Okay, do you have any questions about this? Okay, the next question is how to calculate these integrals. In general case, these are linear integrals. Linear integrals, and linear integral, we know from our calculus that linear integral is quite a difficult math problem, but in this case, in case of electrostatic field, it can be seriously simplified. It can be simplified. And uh, what do you think? How to do this? How to simplify these integrals? Which property of electrostatic field allows us to simplify these integrals? Okay, electrostatic field is potential field. It is potential field, and it means that these in linear integrals don't depend on way from initial to final position. Uh, so potential difference doesn't depend on way from initial to final position. From initial to final position. And so according to this, we can according to this we can find the solution. According to this, we can choose this way. And the way from initial to final position is defined by this vector dr. Defined by this vector dr. So let's choose vector dr according to this condition for the first integral. Okay, and according to this condition, how can we calculate scalar products or dot product of these vectors? How can we calculate scalar or dot product? How do you think? Scalar product or dot product? And we have done today. We have already done very similar thing. We have done very similar thing from for vectors d and ds. Okay, it will be absolute value of e1 e1 multiplied by absolute value of dr multiplied by cosine. And what angle will be here? How do you think? Mhm. 0. Okay. Okay, it will be 0. It will be 0. I agree. I agree that it will be 0. It will be 0. So here we have cosine of 0 degrees. 0 degrees, and we know that cosine of 0 degrees is equal to 1. So it will be absolute value of e1 multiplied by dr, and this will be e. It can be written just as e1 multiplied by dr. So a simple result. And in a very similar way, we can choose for second integral, we can choose dr according to the condition. According to the condition, that e, and from this e2 dr and it will be equal to e no 1, it will be 2 dr. Okay, so we managed to simplify these integrals. We managed to simplify them, and according to this, we can write uh, that this will be equal to this. It will be equal to this. It will be equal to this, but so very similar result, but without vectors. But without vectors. Okay, and after simplifying, we can we can make a substitution. We can make substitution. So instead of E1, we can write Q divided by E epsilon 1 epsilon 0 S. So we can write integral from 0 to d1 from d1 Q divided by epsilon 1 epsilon 0 S d r plus integral from d1 to d1 plus d2 q divided by epsilon 2 epsilon 0 s epsilon 0 s dr. Okay, and how do you think? Uh, does this depend on dr or no? Does this depend on dr? Okay, so it doesn't depend. It doesn't depend. So we can write this value outside of the integral. Epsilon 1 epsilon 0 s integral from 0 to d1 from 0 to d1 dr and plus the same situation will be for second integral. Q divided by epsilon 2 epsilon 0 s integral for d from d1 to d1 plus d2 and dr. Okay, and what can you say about this integral? How to calculate it? No ideas. But maybe you can remember. Maybe you can remember from calculus how to calculate this. Can you remember this from your mathematical analysis or calculus? How to calculate this integral? Okay, maybe you can remember how to calculate this integral. How to calculate this. Maybe you can remember this. Cannot remember. Cannot remember. Okay, but it can be, this integral can be found in the internet. You may just ask Google to find a table of integrals, and here you will get that this integral uh, is equal to x to the power of n plus 1 divided by n to the power of n plus 1 and plus integral constant. Okay, so what to do? What to do with this integral? And this integral can be written as integral of 1 multiplied by dx, and it will be integral of x to the power of 0 dx. Okay, and what can we do? What can we do next? What will be the next step? What will be the next step according to this? How to use this here? How do you think? What will be here? So what will be here according to this formula? Okay. Think 1 plus c. It is similar, but not one, not one, because according to this formula, it will be x to the power of 0 plus 1, 0 plus 1 divided by 0 plus 1 and plus c, and it will be x to the power of 1 divided by 1 and plus c, and it will be x plus c. It will be x plus c. Okay, do you have any questions about this? No questions. Okay, so let's remove some unnecessary things. Let's remove some unnecessary things from the screen. And I just need this result. 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 And okay, and if we write okay, let's try to calculate these two integrals according to obtained formula. First integral will be just equal to r, and here we have r is equal to 0, to r is equal to d1. So it will be d1 minus 0, and it will be just d1. And the second integral, d1 to d1 plus d2, it will be r. Integral limits r is equal to d1, and r is equal to d1 plus d2 plus d2, and this will be d1 plus d2 minus d1, and this will be d2. It will be just d2. Okay, do you have any questions about this? So integrals have been calculated in such way. So from this we have q multiplied by d1 divided by epsilon 1 epsilon 0 s, and plus and plus and plus this, but just it is necessary to change lower index from 1 to 2. Okay, and we need to add these two fractions. To add the two fractions, so it is necessary to derive these two to the same denominator. So we will have q multiplied by epsilon 2 d1 plus epsilon 1 d2, epsilon 1 d2, and divided by epsilon 1 epsilon 2 epsilon 0 s. Okay, do you have any questions about this? Okay, so we have just calculated the potential difference. We have just calculated potential difference for this system. Okay, let's remove some unnecessary things. We don't need this anymore, and we can just remove this. We can just remove this. We can just remove this. So and this, and this, and this, but so this is a potential difference. This is potential difference, connection between charge of capacitor and its potential difference. Okay, and according to this, uh, how to define capacitance? How to define capacitance in this situation? Capacitance. So how to define this value? So in this case, we have quite a simple formula, that allows us to find capacitance. So how can we do this? How can we find capacitance in this situation? Uh, okay, but it will be just result for first layer. I mean general formula for capacitance. According to the definition of this. And moreover, because if we write epsilon 1, epsilon 0 as divided by d1, okay, and what to do with this part? Because we can add them in some way, but it is necessary to derive capacitance from here. What is the general definition for capacitance? It's connection between electric charge and the potential difference. It just can be written as Q divided by potential difference. So after substitution, we will obtain that this divided by this. Divided by this. So this it was the first part. It was the first part of this exercise. The first part of this exercise. And what is the second part? The second part is area bound charge density on the layers interface. Uh, so bound bound area charge density. Okay, it can be done. It can be done with formula. It can be done with formula. Can be done with formula sigma q. This is area bound charge density. Area bound charge density here, and it will be P1n minus P2n. P2n. What is P? P is a polarization vector. Polarization vector, and for isotropic dielectric, it will have the same direction as vector D. And here we have P1, and here we have P2, and here we have P2. Okay, and the angle between these vectors and a layer interface is the right angle. And according to this, we have that P, for example, P1n is equal to absolute value of P1 according to the picture, and it will be P1. And in the same way, P2n is equal to absolute value of P second, and is equal to P second. And so from here we can define that it will be just P1 minus P2. Okay, and how to define this absolute values of polarization vectors? We can use this result. And from here we have that, for example, we can just remember that P1 P is equal to kappa epsilon 0 E, and it will be epsilon minus 1. It is from electrostatics. We have talked about this on our previous lessons. So here we have E. But the electric is isotropic. So we can write from here P is equal to epsilon minus 1 epsilon 0 e. So 0 e. Okay, and from this we can find that P1 is equal to epsilon 1 minus 1 multiplied by epsilon 0 q divided by epsilon 1 epsilon 0 s. On 1 epsilon 0 s, and this will be equal to epsilon 1 minus 1 divided by epsilon 1 q divided by s. And very similar situation for second vector p2. It will be equal to epsilon 2 minus epsilon minus 1 epsilon 2 q divided by s. Q divided by s. So from here we obtain that this is equal to this value. This is equal to this minus this. Minus this. And from here we can write that epsilon 1 epsilon 2 minus epsilon 2 minus epsilon 1 epsilon 2 plus epsilon 1 divided by epsilon 1 epsilon 2 q divided by s, and this is equal to epsilon 1 minus epsilon 2 to q divided by s. Q divided by s. And what do we need? We don't know electric charge, but we can define this charge from here. Q is equal to S multiplied by potential difference and divided by epsilon 2 d1 plus epsilon 1 d2. Okay, and let's make substitution, and finally we will get that epsilon 1 epsilon 1, I mean epsilon 1 minus epsilon 2 epsilon 0, so s was vanished, and epsilon 2 d1 plus epsilon 1 epsilon 1 d2. So this is the answer for the second part of this exercise. Do you have any questions? Okay, and the next homework will be from electricity and magnetism. Electricity and magnetism. From electricity and magnetism. Exercise number 13. Exercise number 13. Okay, do you have any questions? No questions. Okay, if there are no questions, so thank you for your attention, and I hope to meet you next week on Wednesday. Have a nice day.